Good day, everyone. I'm Mr. Michael. Today we shall be looking at introduction to physics subject, and we shall be diving into the concept of physics. All right. Without further ado, let's dive into this. Okay. At the end of this class, we shall be looking forward to these objectives. Firstly, to define what physics is, to state four careers prospect in physics, and also for application of physics. We shall be looking at the definition of fundamental quantities and fundamental units. And lastly, we'll learn how to obtain the dimension of physical quantities. All right, let's dive into this definition of physics. Physics as a subject is one of the scientific subjects, and it deals with the scientific study of the properties and interaction of matter and energy. So when you are looking at how matter interacts and they are linked to energy, then you are already studying physics. You're already performing physics. It's a natural science that based on experiment. We also measure in this subject, and we do mathematical analysis also with the purpose of finding the quantitative physical laws. That's how we do all of this. The experiment, the measurement, and the mathematical analysis are all for the purpose of finding quantitative physical laws. This subject involves measurement of physical quantity. Basically, we deal with a lot of measurement. All right, and it is classified into two branches. We have the classical physics and we have the modern physics. So under the classical physics, we have the mechanics, the heat and temperature, we have wave and sound, we have light and optics, electricity, magnetism, and electronics. And under modern physics, we have atomic physics and nuclear physics. Why it is classified into classical and modern is that this later one came in later the years after the first branch. Later part of the year, modern physics was discovered, and then it was now categorized under modern physics. Okay, and then the application we can apply physics in health sector. The thermometer we use in the hospital, the clinical thermometer, the X-ray machine, and other tools and machines that are used in the hospital are under health. They are under the application of physics too. Then we also have it applied in transportation. The motor vehicle that we use today is invented through the understanding of physics. The bicycles, the motorcycles, the aeroplane, any type of means of transport you can think of, they are all the idea of physics. And in the entertainment industry, make use of cameras, television, radio. All of these gadgets are all produced with the knowledge of physics. Now, as a physicist, or when you study physics, you can become a physicist as a career. You can also be a researcher in the area of physics. You can be a geophysicist. You can be a radiologist. You can also be a telecommunicationist. Then you can be various kind of engineers, computer engineer, mechanical engineer, electronics engineer, electrical engineer, civil engineer, architects, quantity surveyor, chemical engineer, chemical engineer, and so on and so forth. So many prospects in this subject. And now for you to study this subject, you must know the ABC of this subject. And this ABC are what we call the fundamental quantities and the fundamental unit. Now, the fundamental quantities are just the basic quantities that are independent of other quantities and cannot be defined in terms of other quantities. In other words, other quantities you can mention at all depend on them, and they have their respective fundamental units. So the fundamental unit are the basic unit, just like the fundamental quantity are the basic quantity. So fundamental unit are the basic unit in physics, upon which all other units depends on. And they are the unit of the fundamental quantity. So every fundamental quantity has its respective fundamental unit. So as a physics student, if you don't know these fundamental quantities, you will definitely not be able to function well or understand this subject because it is the ABC of the subject. Now let's talk about some of the examples of fundamental quantities and unit. Basically, fundamental quantities are just 7 in number. We have them as length, time, mass, electric current, temperature, amount of substance, luminous intensity. And each of these quantities have their respective fundamental unit. For length, the fundamental unit is meter, by symbol is small letter m. For time, the fundamental unit is second, and by symbol is small letter s. For mass, the fundamental unit is kilogram, and by symbol is kg. For electric current, the fundamental unit is ampere, by symbol is capital A. For temperature, the fundamental unit is Kelvin, and by symbol is small letter K. For amount of substance, the fundamental unit is mole, and by symbol is MOL. And lastly, for luminous intensity, the fundamental unit is candela, and by symbol is CD. So these are the 7 basic fundamental quantities that we must know if we must enjoy the subject with their respective fundamental unit and their respective abbreviation or symbol. We also refer to this fundamental unit as SI unit. The word SI simply means Système International. It's a French word which means International System of Units. So all this unit of all these units that we have here as fundamental unit are also called SI unit. It means that they are universally accepted all over the world. Okay. Now the opposite of fundamental unit is derived unit. From the name, derived unit. Derived quantity, I mean. Derived quantities are actually obtained from fundamental quantities, and their respective units are also obtained from fundamental unit. So derived quantities are those obtained by simple combination of fundamental quantities. And then derived units are those obtained by simple combination of fundamental units. So when you combine 2 or more fundamental quantities, you get derived quantities rather. And when you combine 2 or more fundamental units, you get unit, you get derived unit. Okay. So some of the examples of derived unit and quantities, we have them here. We have quantities, we have area. By formula, we know area is length and breadth, but derived unit of area is meter square. For volume, we know by volume, the formula is length and breadth times height. The derived unit for volume is meter cube. For density, by formula, we know it's mass over volume. The derived unit for density is kilogram per meter cube. For velocity, by formula is displacement over time. And by derived unit, we have it as meter per second. For acceleration, by formula is a change in velocity over time, and by unit is meter per second squared. For force, the formula is mass times acceleration, and by unit it is Newton or kilogram meter per second squared. Now there's another aspect we need to know concerning physical quantity, and that's called dimension. Dimension of a physical quantity is the way it is related to the quantity of mass, length, and time. So any physical quantity that has mass, length, and time, we usually use these 3 symbols, MLT, to find their dimension. Now, in advanced level, in A level, we also include electric current and time. So dimensions are just the way physical quantities are related to these 3 quantities: mass, length, and time. In this case, we now represent mass with capital M, length with capital L, and then time with capital T. Then for JAMB students, we include current, which is capital I as well. Okay, so let's see some of the dimension of some quantity. For velocity, the dimension for velocity is Lt to the power minus 1. Okay, because velocity unit is meter per second. And meter is for length, so L, length represents L there, while the second there is capital T. You could see that ms is replaced with LT, negative power minus 1, because m there is meter, which is length, then second there is time, which is T. For acceleration, its unit is meter per second squared. Since meter is length, so we have length, and second is T, so capital T minus 2. So the dimension for acceleration is L T to the power minus 2. And for force, it is by unit is Newton. The formula is MA, but by dimension, it is ML T to the power minus 2. For momentum, the unit is kilogram meter per second, but the dimension is ML T to the power minus 1. Dimension have nothing to do with any other thing than LT and M, okay? For density, it is kilogram per meter cube, but by dimension, it is ml, is per minus 3. For pressure, by unit, it is Newton per meter square, but by dimension, it is ml is per minus 1 and t is per minus 2. Okay, there's more to this dimension that we need to know. Okay, let's see an example here. It said, at what respective values of x, y, and z will the unit of force be dimensionally equivalent to m with the power x, l with the power y, and t with the power z? So meaning that we are looking for the value of x, y, and z. Okay, x is unknown, y is unknown, and z is unknown. Now, the dimension for force, remember we are looking for the value of x, y, and z, but we are told to use this unit of force to determine it. So by dimension of force, it is ml to the power minus 2. Now, we are given this expression here. So this expression is equivalent to the dimension of force according to the question. So m power x, l power y, and t power z equals the dimension of force, which is ml to the power minus 2. Now going forward again, m with power x, l with power y, and t with power z equals, now m alone has the power of 1 mathematically, okay? Any letter without the power has a invisible power of 1. So I'm invisible now. So this m become m with the power 1, just like L2 become L with power 1, and then t still have it minus 2. Now we're going to be equating the one with the same base. If we look at it now, we have m with the power x on the left and m with the power 1 on the right. Since we have m at the same base, so their power will equate each other. So x equals 1, okay? And for L, x power y, and on the right, L power 1. Therefore, y equals 1, 2. And then for z, so t to the power z here, t to the power minus 2. So since t are the same base here, so z equals minus 2. Okay, z equals minus 2, as you can see there, equals minus 2. Okay, so that's it. Very simple question. Okay, let's see another one and see how simple it is. Example 2. It says, at what respective values of A, B, and C will the unit of impulse be dimensionally equivalent to m to the power A, l to the power B, and t is to the power C? All right, just the same way we have it in example 1. We are looking for A, B, and C. Impulse dimension is m, l, t to the power minus 1. And since we are given this expression to equate it with it, so this expression is equivalent to impulse, which is ml t to the power minus 1. So going down further, m with the power a, l to the power b, and t to the power c equals, introduce the power of m and l, so we have it to be 1, 1. And now from there, we can now say that a equals 1 since they have the same base of mm, and b also equals 1 since they have the same base of ll. C equals minus 1. So this will be C. This is our C. So C equals minus 1 since they have the same base of T and T. Okay, so very simple as well. All right. Let's see another example on this. Let's start the example on this. Example 3 is kind of a complex question for us. So let's see how it goes. Here it says a sphere of radius r moving through a fluid of density rho with velocity v experiences a retarding force F given by this equation. F equals K, R is power A, rho is power B, and V is power C, where K is a non-dimensional coefficient. Okay, use the method of dimension to find the value of A, B, and C. Again, we are looking for A, B, and C. And we are given the equation here, we have to follow the instruction. We are given the equation here, and we have to use dimension analysis to find the value of A, B, and C. Okay, we already know that F is force, so like substituting the value of the dimension for force in the next stage, we have it to be ml to the power minus 2, right? Now let's take note of the expression on the right side of the equation. K is non-dimensional, so we don't need K in our dimension analysis here. So I've taken out K from the equation. Now L is the radius as given here, and the dimension for radius is L. R rather is a radius, and the dimension for radius is L. So we have L to the power A. This rho we have been told is density, and density is mass over volume. So by dimension, the dimension for volume for density rather is ml to the power minus 3 all with the power b, because it has the power of b here. And then for velocity, the dimension of velocity is L to the power minus C, to the power L to the power minus 1, everything to the power C here, you could see. So this is the dimension for velocity, L to the power minus 1 with the power of C, alright? Now the next step, we need to introduce the power of M and L, that's M with the power 1, L to the power 1, and 2 to the power minus 2 equals L to the power A. Then of course we repeat everything as written here. So the next step again, M to the power 1, L to the power 1, and 2 to the power minus 2 equals L to the power A. We need to expand what is here. So by the time we introduce the power of B, we have M with the power B, we see it here, and L to the power minus 3B. And when we expand what is in this other bracket, we have L to the power C and 2 to the power 1 minus 1C. Still going forward, so M with the power 1, L to the power 1, 2 to the power minus 2 equals. Now we're going to arrange these the way it is on the left. Since we have M at the fourth letter, so we bring M at the fourth letter on the right side. So we have M with the power B. Then all the L, collecting the like terms, all the L comes together. So we have L to the power A, L to the power minus 3B, and L to the power C. Then, of course, T to the power minus 1C. Now, M to the power 1, L to the power 1, and T to the power minus 2 equals M to the power B. I'll apply the law of indices here. Since they have the same base of L, so one L will be written, and all the power will be added up together. And that will be A minus 3B plus C. Then for T to the power minus 160 remain. Now equating the base, so M with the power 1 on the left and M with the power B on the right, equating them, since they have the same base, then their power becomes equal. So from here now, B equals 1. B equals 1. Okay, so moving forward, let's see, move forward for the next one. The next one is we have T, we have T to the power minus 2 on the left and T to the power minus 1C on the right. So equating them, so we have T to the power minus 2 equals to T to the power minus 1C, and there we have minus 1C equals to minus 2, and then C become 2. Okay, so that's 4. So we've obtained the value of B and C now. So we have A to be to obtain. So now to obtain A, we need to equate the power of the base of L on the left to that of on the right. So on the left hand side we have L to the power 1, and on the right we have L to the power A minus 3B plus C. So we need to equate their power for us to obtain the value of A. So moving forward, so we have it here. You see L to the power 1 equals to L to the power A minus 3B plus C. Now when we do that, we will be having 1 equals to, we'll be having 1 equals to A minus 3B plus C. Now that we've obtained the value of B to be 1 and the value of C to be 2, so we substitute them into this equation here, And when we do that, we'll be having 1 equals to a minus 3 into bracket 1 because our b is 1 plus 2 because our c is 2. And when we simplify this, our a will be equals to 2. That's all for example 3. Okay, so we shall be drawing the curtain here. But before that, I would like to give you the evaluation here. The following, I would like you to attempt them and see if it is be able to solve the problem. So we're going to draw the curtain here. Thank you for listening, and bye for now.